Q. Okay, so, all right, so let's start with this group, my favorite group, SL2Z. And you can look at its quotients, SL2 Z mod n, and we look at this kernel, and these are called the classical principal congruent subgroups of level n. And so it's very classically known that if you look at the quotients of the upper half plane by these congruent subgroups, so these are these modular curves, they have moduli interpretations as elliptic curves, say E over C, in this case equipped with a isomorphism between its n torsion and Z mod n cross Z mod n, up to isomorphism. Okay, so such a data of an isomorphism between the n torsion, so you would call this a gamma n structure, and this can be seen as, well, you can look at this as a firstly you have a natural isogeny from the elliptic curve to E mod its n torsion, and the dual isogeny gives you a so this isogeny would basically give you a Z mod n cross Z mod n torsor, by which I just mean a Z mod n cross Z mod n Galois cover of E mod its n torsion, and the dual isogeny would, well, I suppose it would technically give you a mu n cross mu n torsor. Okay. All right, so on the other hand, this group SL2Z has lots of noncongruence subgroups, by which I mean just subgroups finite index subgroups which don't contain one of these gamma n's. And the question is, do these noncongruence modular curves, so quotients of the upper half plane by these noncongruent subgroups, do these H mod gammas have moduli interpretations as well? Okay, and I should note that by Bailey's theorem, in fact, every smooth projected curve defined over a number field can be realized as the compactification of one of these H mod gammas. And so really we'd like to find moduli interpretations that are sort of compatible with this uniformization by the upper half plane by and quote, modded out by some finite index subgroup of SL2Z. So ideally we'd like to define moduli interpretations in terms of sort of level structures on elliptic curves. Okay, so this is what we'll do. And to do this, we'll sort of go back to this picture, and we'll note that in the congruence setting, all these congruence modular curves, they are moduli spaces for elliptic curves equipped with some sort of unramified torsor, some abelian, in particular, unramified torsor. And now you could ask, well, what if you allow for some ramification? And so in general, when you allow for ramification, you have this new sort of continuous piece of data called the ramification divisor. But in the case of elliptic curves, it comes with a canonical divisor given by just its identity section. And so we'll just sort of allow for ramification at the identity. And why does this give us new things? Well, new covers. Well, so if you think of an elliptic curve as just the fundamental domain given by some lattice, and these would be two generators of its fundamental group, then if you sort of go all the way around, then this is the commutator of the two generators. And the fact that there is no puncture means that the commutator is 0, so the abelian, so the fundamental group is abelian. But on the other hand, if you puncture it somewhere, then the fundamental group is just freely generated by these two generators. And so the fundamental group of a punctured elliptic curve is F2, which has lots of non-abelian quotients, and so you get lots of non-abelian level structures. So let's fix a finite two-generated group G. So we'll talk about, we'll essentially define the notion of a G structure on an elliptic curve. So on M1, this is just the moduli stack of elliptic curves. In this case, let's view it over schemes where the order of G is invertible. So we give this the Étale topology and making it into the big Étale site. And from this, M1 inherits a topology. And so the easiest way to define G structures is just by defining a sheaf on M1 with the inherited topology from this. So from this, we'll define a presheaf just given by, okay, so what are the objects of M of 1, the moduli stack of elliptic curves? Well, these are just elliptic curves over S. And to any elliptic curve over S, we'll associate, so let's call this H sub G. We'll associate the set of, the set of G torsors on the punctured elliptic curve. So this is just the elliptic curve minus the identity section, up to isomorphism. And I suppose I should say geometrically connected. Okay, and so this gives us a pre-sheaf, and we'll just let H, we can look at its sheafification. And it turns out that by sort of playing with fundamental groups, we found that this sheafification is finite locally constant on M1. And so in particular, this tells us that we have a, so this corresponds to a stack, which is finite. So sort of by looking at its étale space, it corresponds to a stack which is finite étale over M1, which is called MG. And the objects of this stack, so the objects of M1 are just elliptic curves over S. The objects of this stack will be elliptic curves over S equipped with some alpha, where alpha is, by definition, an element of sort of this sheaf. So I should note that if G is center free, if G doesn't have any if its center is trivial, then in fact we don't need to do this sheafification, and so really alpha is just literally a G torsor on the punctured locus. Okay, so this is sort of the easiest way to define G torsors, but it's not so amenable to calculation. And so to do, how much time do I have? So it's 2:07, perfect, okay. So instead, perhaps another way to look at it also is, well, so in the simplest case where you have an elliptic curve over a field K, say characteristic 0, then we have this homotopy exact sequence of fundamental groups, circ over K bar, where this GK is the absolute Galois group of K. And from this sequence, you get an action of the absolute Galois group on pi 1 of E circ over K bar. So I should note that this is just the free profinite group of rank 2. So I mean, canonically associated to this exact sequence, you have an outer action of GK on this, or you could pick tangent to base point if you wish to get an actual action, but that's not so important. And from this, then the objects. So the alphas here are just, so I should have said the alphas are called G structures. So the objects of MG are E over S alpha, where alpha is now can be viewed as an element of this set of surjections from pi 1 from its geometric fundamental group to G, modulo conjugation in G. And then we require that we're only looking at GK equivariant surjections. So here G is just given the constant, the trivial action. Okay, so basically this is sort of a combinatorial description of the objects of a G structure. So a G structure is really just combinatorially given by a surjection from the fundamental group of the elliptic curve, or of a geometric fiber of the elliptic curve to G modular conjugation. Okay, so how does this relate to modular curves in SL2Z? So perhaps I should go back to this picture, and we can look at this situation over C. So I can base change to C. And then over C, this is really just sort of this orbifold quotient of the upper half plane by SL2Z. And this thing has pi 1 equal to, so I guess étale pi 1 equal to SL2 of Z profinite completion. And so to understand this, since this map is finite étale, to understand sort of the structure of MG, we want to understand the structure of the fundamental group, or the monodromy action of the fundamental group of the base, which in this case is SL2Z on a geometric fiber? Well, a geometric fiber is given by, so first you pick a geometric point in a base. And what is the fiber up here? Well, from this description, right, the fiber up here, so I mean, from the description of the map, this is just the forgetful map. And so the fiber will just be the set of possible G structures, the set of possible alphas. And from this description, in this case, we're working over C, so there's, which, so it doesn't have an absolute Galois group. This is really just given by surjections from the fundamental group to G modulo conjugation. Right, so this geometric fiber is really just epi surjections from pi 1 of the circ over C to G modulo conjugation in G. And this as a set, well, OK, so this is F2 hat technically, but this as a set, since any surjection from F2 to the finite group factors through its profinite completion uniquely, this as a set can be identified with surjections from just F2 to G mod conjugation in G. And now we have this we have this exact sequence from group theory. So if you take the discrete group F2 and look at its automorphism group, well, it maps surjectively onto the automorphism group of its abelianization, which is just GL2Z. And it's a classical theorem of Nielsen that its kernel is precisely the inner automorphisms. OK, so that means that we can identify GL2Z with basically automorphisms of F2 up to conjugation. So in other words, outer automorphisms of F2. And inside GL2Z, we have SL2Z. And SL2Z can thus be viewed as outer automorphisms of F2. And one can prove, there is something to prove here, that this is precisely the action that, that you get. So in other words, the way the SL2Z viewed as the fundamental group of the moduli stack of elliptic curves over C acts on the geometric fiber of such a, of MG is precisely via its action on the domain here, outerly sort of on this set, since here we're quotienting out by conjugation. Really all you need to define an action on this set is an action on F2 up to conjugation, and that is precisely what we have. So what this tells us is that these MGs, so these MGs are just, over C at least, are just sort of disjoint unions of modular curves, where each gamma is basically given by, corresponds to an SL2Z orbit on this set. And if for every sort of, if you pick a representative of all these orbits, then the gammas are just the stabilizers of these representatives. OK, so I have 2 minutes. So basically, this is the story. And one could ask, well, OK, so I guess right now I'm trying to figure out what you can do with this. One point is as follows. So say H mod gamma has genus 1, and say f of z is a weight 2 cusp form, so a noncongruence cusp form, so just defined in the very classical analytic sense, cusp form for gamma. And say this is equal to, it's got q expansion a of n, q to the n. Then, sort of modulo some technical issues, you have these congruences, these so-called ASD congruences. ASD stands for Atkin and Swinnerton Dyer. So this is 0 mod p to the 1 plus the order, the evaluation of n. And so from these congruences, so these AMPs are just the Fourier coefficients, and this AP is just the, so modulo technical difficulties, this AP is the trace of Frobenius acting on sort of the, say, the moduli theoretic model of H mod gamma. And what do these moduli theoretic models, so in other words, the APs count the points of these modular curves mod p. And what do these points represent? Well, again, under certain technical difficulties, or up to technical sort of assumptions, these points are basically just elliptic curves over FP with equipped with a certain G-torsor, right? And these G-torsors, so from this description here, these G-torsors come from, can be are given by essentially this set. And this set, by its definition, it involves this action of the absolute Galois group, the Galois action on this geometric fundamental group. And this is sort of a very mysterious action, and this really sort of goes into Abelian geometry. And in fact, I think so for example, the data of this action on the geometric fundamental group is enough to actually recover the isomorphic type of the original curve up to, well, the isomorphic type of the elliptic curve. So the data of this action is very strong, and I don't think there's a single example actually of a hyperbolic curve over a finite field where even where the action of Frobenius on the fundamental group is actually known. So I guess that's it. Sorry.